Let's do some practice problems with acetals and ketals. And then we'll talk about an important use of acetals and ketals in industry and in the chemistry field in general. So first, doing some practice, we're starting with acetophenone. We have trace amounts of H2SO4. We know that's a strong acid. And we have methanol as our solvent. Well, if I see all of this, I see we have a ketone, an alcohol, and an acid catalyzed reaction. This tells me that the carbonyl carbon from our original ketone will now be bonded to two alkoxy groups. Both of the alkoxy groups come from the alcohol, the methanol. So now that carbonyl carbon is bonded to two methoxy groups, each coming from methanol. Let's do another practice question. We'll have another ketone. You could make these aldehydes, they would follow the same process. And let's say we have this diol. We'll have a 3-carbon chain in between the alcohol groups. And then some acid present in solution. Well, when we go through this reaction, we know that we'll have an alkoxy group from an alcohol, the solvent. We'll say this is an excess. Just like a solvent would be an excess. Now, instead of having two of these alcohol separate molecules bonding to the carbonyl carbon, we could have one of the OH groups bonding to the carbonyl carbon and the other from the same molecule, the same diol, bonding to that carbonyl carbon as well. So that would look like where our carbonyl carbon is. We have one oxygen that has 3 carbons bonded to another oxygen, and that one's also bonded to that carbon that was part of the carbonyl carbon. That might be difficult to see. I'll show an abbreviated version of the mechanism. So if our first step is just add, well, it's not our first step, but after the first couple of steps, we've added one of the alcohols from that diol. We would have let's see, we've got this oxygen, we'll say, is from the diol. So we'll trace these atoms in pink here so we can emphasize that here. Oh, I'm missing a carbon. Let me add that carbon in. Okay, so we've done the nucleophilic addition where we have added one of the oxygens from the diol. Let's say we've already protonated the OH, so we have our good leaving group. This is going to leave. We form a double bond between the oxygen from the alcohol and what was the carbonyl carbon. We've lost water, and let's keep these pink. Now that we already have this alcohol group right here, close to that carbonyl carbon, or that carbonyl-like carbon, the carbon with the double bond, this alcohol oxygen can easily form a bond to that carbon, and then we break that pi bond. And then we get that product with that ring. So I've skipped some steps. And I've skipped some steps here. We could certainly write out the entire mechanism, but really what I'm trying to show you here is how we get that ring as that product. By having the alcohol that's getting added is a diol. And this is how acetals are often used and ketals are often used in industry. We call them protecting groups. So let's say we have, we'll just label this part acetals as protecting groups. And let's say we want to carry out this reaction here. Okay, so if we want to carry out this reaction, let's look at what's changing here. The ketone part of the molecule is not reduced. That has not changed. But here we have a carboxylic acid and that has been reduced. If you see the difference between the two molecules, our carboxylic acid is now an alcohol. And that group has been reduced. Well, the reagents that will reduce a carboxylic acid, let's redraw the molecule here. Our reagents that reduce the carboxylic acid is our lithium aluminum hydride. So we have lithium aluminum hydride in one step and then some acidic, let's say H3O plus as a second step. That will reduce the carboxylic acid, but it will also reduce the ketone. So if all we're adding is the lithium aluminum hydride, then we're not getting our desired product. We're getting a diol, 2 alcohol groups. So this directly is not sufficient to achieve the goal of the reaction, which was a molecule that has both a ketone and an alcohol, where we've reduced the carboxylic acid but not the ketone. These reagents reduce both the ketone and the carboxylic acid. Now, we can prevent this from happening by adding an acetal as a protecting group for the ketone. So if we add an alcohol, especially that diol, those are often used in the chemistry field to form a protecting group, that will react with the ketone. Then we'll still have the carboxylic acid, we reduce the carboxylic acid, and then we can remove the protecting group and we get our desired product. So let's look at what this reaction scheme would look like. We start with our original, let's say, use of protecting group. Starting with our original ketone and carboxylic acid molecule, if we add a protecting group, again, diols are often used in this case with some acid, or we could add some base. Then we would end up, now we're not showing the entire mechanism here, we're just looking at the major intermediates. Where the ketone was, we'd have that ring. We're now at that point, we no longer have a ketone. We have a ketal part of the molecule. So now if we add the lithium aluminum hydride and then acid in a second step, the only part of the molecule that can now get reduced is the carboxylic acid part of the molecule. So we keep the ketal as is. And we've reduced the carboxylic acid. Now, ketals and acetals are formed through reversible reactions. So with the correct conditions, in this case, if we add water and some acid, we then remove, we're promoting the formation of the ketal, which is a reversible reaction. We promote the reaction to go in reverse, where the ketal is then favored to form then the ketone as it started off with. So we're essentially removing the protecting group. We go back to our ketone and we have achieved our desired product. That's supposed to be a little check mark there.